So continuing with our theory topics, let's see the working principle of the barometer. So barometer basically consists of a vertical tube which is flipped, and it's the free end, the open end, it is lowered or immersed in a liquid. So if a tube lower end is immersed in a liquid which is exposed to atmospheric pressure, um, so this is a liquid layer, so this is exposed to atmospheric pressure, and here we have a tube, and with this free end it is immersed in the liquid, and if the air is exhausted from the tube, so the air which is over here stored inside the tube, this has to be removed and the liquid will rise in it. The liquid will definitely rise in the tube, and this rise is given by Y. And if the air is completely exhausted, the only pressure on the surface of the liquid in the tube would then be that of its own vapor pressure. So the pressure at here inside the tube will only be the vapor pressure, and the liquid would have reached its maximum height. So let's write the pressure equation. We know pressure at point O, which is inside the tube, which will be same as the pressure at point A, which is atmospheric pressure. And if the cross-sectional area of this tube is capital A, we can convert this pressure into force by multiplying it by the area. So pressure at point O, which is atmospheric pressure, multiplied by A, so as over here, and as we're going upward, so pressure would be reduced, so it is minus the density of the liquid, rho g or gamma, into gamma y, and into the area, the cross-sectional area, to convert to force. And over here the pressure is vapor pressure, and since the vapor pressure is taken as negative, so it is minus vapor pressure into cross-sectional area. So rearrange it, we'll get atmospheric pressure is equal to gamma y plus vapor pressure, dividing it by area. If the vapor pressure on the surface of the liquid in the tube were negligible, if the vapor pressure is ignored, then we'll get atmospheric pressure is equal to gamma y. So this is basically the principle which is used for measuring pressure through a barometer, that we note the rise of liquid inside the tube, and that rise that actually indicates the pressure. So from this animation as well, you can understand that the atmospheric pressure is equated with the rise of liquid in the tube. And we also know that at hilly areas where the atmospheric pressure is lowered, so this rise inside the tube will also be lowered. And as we have seen earlier as well, the atmospheric pressure is 101.325 kPa, and if we use water to measure this atmospheric pressure, this rise will be almost 10.3 meters of water, which is very large. And if we simply replace this by mercury, which is 13.6 times denser than water, so this rise would be only 0.75 meters. So the instrument will become quite compact, and this is the reason we use heavier liquid to measure pressure, atmospheric pressure. And the corrections of capillarity and vapor pressure should be applied. So let's see the working of a Bourdon gauge. Gauge pressure or vacuum pressure, they can be measured by using Bourdon gauge. In this gauge, a curved tube of elliptical cross section which changes curvature, which changes in pressure inside the tube. So this is the front face of the Bourdon gauge, and behind it we have this geometry. So this end, this is connected to a pipe, And like over here in the schematic diagram is shown, this pipe is linked with the point or the pipe for which we want to measure the pressure. This is the Bourdon gauge, and it consists of this elliptical shape tube. So this tube basically it changes shape with the change in pressure, and it is linked with this geometry through this lever arm, and it is linked with this needle. So as we connect the Bourdon gauge with the pipe and we have change of pressure, the liquid it will enter the tube, and this tube it changes in shape, it expands or compress according to the change, and eventually this needle it moves, and it directly gives us reading in psi. This outer scale is given in psi. So the moving end of the tube rotates a hand on a dial through a linkage system. So they're actually talking about this linkage system, which connects this tube with the needle on the gauge. A pressure or vacuum gauge combined into one is known as compound gauge. So this Bourdon gauge is basically a compound gauge because it can measure both gauge pressure and vacuum pressure. So here I want to show you this animation which shows the working, and you'll understand it as the pressure, the water it rises into the tube. Because of pressure, this Bourdon gauge tube it will expand, and eventually this needle moves, indicating the change in pressure. So some correction has to be applied for Bourdon gauge depending upon the location where the Bourdon gauge is attached to the pipe. So let's explain the figure in which the Bourdon gauge it is attached to the pipe, and it is at a height of Z. So basically Bourdon gauge it gives you pressure inside its center, but we require pressure at the center of the pipe. So this elevation correction has to be applied. So pressure inside the pipe PA would be equal to the gauge reading in PSI plus, as we going downward, so plus gamma Z. As over here, when the pressure is in PSI, PA, so it will be gauge pressure in PSI plus gamma Z. So this 144, this is basically the correction factor for SI units. We know 1 foot is 12 inches, and 12 into 12 is 144. So you do not need to consider it if you're using SI units. For SI units, we require no correction factors. So these factor 144, this is not required for SI. So I would even say that you can ignore this 144, simply try to understand this equation. Because we want pressure inside the pipe, and the Bourdon gauge is giving you at its center, so the pressure at the pipe would be gauge pressure plus gamma Z. Now if vacuum pressure is measured using this pipe and it is given in inches of mercury, so this will be gauge reading in inches of mercury. As it is vacuum pressure, so it is already negative, right? And as we go downward, so pressure has further increased, so the increase should be in minus. So minus the vacuum pressure reading inside the Bourdon gauge minus gamma Z will give you the vacuum pressure at point A. Again, these are the correction factors. You can simply eliminate it and just focus on this expression. So these elevation correction factor, they basically they change or they depend upon the location of the gauge. If the gauge is above or below the point, what we have seen the case is when the gauge is above the pipe, so it has to be added. Now what if the gauge is below the pipe? had the gauge been over here, it is giving you the reading. So in this case, the pressure at point A would be the gauge reading minus gamma z. Similarly, the change would be in the vacuum as well. Hope so you have understood it. So moving on. Now let's see the last topic from the slide, which is pressure transducer. A transducer is a device which transfers energy in any form from one system to another. Like the Bourdon gauge, which we have just seen, is an example of a mechanical transducer in that it has an elastic element that converts energy from pressure system to a displacement in the mechanical measuring system. Then an electrical pressure transducer, it converts the displacement of a mechanical system, usually a metal diaphragm, to an electrical signal, either actively if it generates its own electrical output, or passively if it requires an electrical input which it modifies as a function of the mechanical displacement. One of the form of the pressure transducer is an electrical strain gauge, which is attached to a diaphragm. As the pressure changes, the deflection of the diaphragm changes. This in turn changes the electrical output, which through proper calibration can be related to pressure. Such a device, when connected to a strip chart recorder, can be used to give a continuous record of pressure. In lieu of strip chart recorder, the data can be recorded at a fixed time interval on a tape or disk through a computer data acquisition system, or